All right, we'll try to wrap up the chapter chapter 4, which is time response. Did you complete the last lab? Okay. There is something you need to learn about that lab, which is relevant. We'll discuss it as part of lab session. Okay. From the exam point of view, from the assignment point of view, so you might be given such a system. Example. So we will discuss a rotational system, but you might be given a electrical system or a translational mechanical system. And so here the question could be something like, find J and D to yield a 20% overshoot. And a settling time of 2 seconds. Okay. So the first thing you're going to do when you're asked something like this, you're going to find the transfer function. Okay. So the transfer function here is, so the input is the torque and output is theta. So we have theta s over T of s is equal to J theta double dot plus D theta dot T it is 1 over J square theta of s plus ds theta of s plus 5 theta. Right? Find J and D. Okay, so it's J square plus ds plus 5. Okay. Now here what do you do? So this is also equal to 1 over J into a square plus D over Js plus 5 over J. Okay. This is G of s. Now when you're asked to do something like this, this will be, you cannot really find the overshoot and settling time for a system without specifying the input. So you'll be given, let's say, find to yield a 20% overshoot and a settling time for a step response, right? So again, your C of s, so T of s is essentially 1 over s, implying C of s is equal to 1 over J into s square plus D over Js plus 5 over J. Okay. So what do you do when you're given something like this? If you're asked to find J and D, compare this to the general second order system, right? What is it? right? Omega n square over S square plus 2 zeta omega n S plus omega n square. Okay, so omega n square is what? 5 over j. Okay, implying omega n is equal to root of 5 over j, and 2 zeta omega n is equal to d over j. Okay, which means zeta is equal to 1 over 2 d over j j over root 5. So zeta is equal to d over 2 root j. Okay. Now what do you do? Right. So what is, you're given percentage overshoot, okay, and there is an expression for, obviously there's a relationship between percentage overshoot and the damping ratio, right? Or there is an expression for damping ratio in terms of percentage overshoot. I think it is. So this is also equal to minus natural log percentage overshoot over 100 divided by pi square plus and omega n, or settling time, is what? 4 over zeta omega n, right? Or implying omega n is 4 over zeta settling time, correct? Yeah. So all you need to do is you need to substitute these and figure out, you know, omega n, right? And you know settling time. So from this, what is the unknown here? Let's see which one is. If you look at this, can you figure out an expression for omega n so you have this zeta ds, this is root of 5 over j. You don't know what j is, you don't know what zeta is, correct? But you know. Right. So this is, so what you have, you're going to end up with 2 over zeta is equal to root of 5 over j, right? Ts is given, zeta is not given, damping ratio. So you equate these two. You can express zeta in terms of j here. It's also d. Right. So you can just use this expression to figure out zeta. That's right. So for example, just ignore this for a while. Yeah, if you look at this one, everything is given in there, right? So its percentage overshoot is 20. Okay. You get a value for zeta, and if you substitute that value of zeta, you're going to get j. And then if you go back, j is known, zeta is known, you can get d. Okay. So you'll be given such a problem to figure out. See, what you're trying to do here is you're trying to design a particular system so that you get these parameters. Okay. So these are the two equations which will give you values for. All right. So this, if you look at this this chapter, it says time response of first and second order system, right? What has been the dominant component which determines this response in this? Keep going. Right. What else? Given such a system, right? Given second order system, Right. Roots or poles determine the response of a particular system, and that's what you're trying to do in the lab as well. In your MATLAB, when you're trying to compare, see what you're trying to compare there. One, you're increasing the real part and of seeing how the response is. The other you're doing is you are increasing the imaginary part and looking at how the response is. You can keep the damping ratio the same, which means you, if you do a pole plot or a pole zero plot, so if you increase the real part, the poles are going to increase in that direction. Okay? If you increase the imaginary part, the poles are going to increase in that direction. Okay? Now if you have something like this line actually represents this theta. Remember I told you theta, cosine theta is essentially the damping ratio. Okay. As long as the theta remains the same, the damping ratio remains the same. That's kind of a linear relationship. Okay. As long as theta remains the same, the damping ratio remains the same. Although you're changing the poles, the value of the poles, and you can impact this in real world or in control systems. These poles mean something. You can add poles. Mathematically, they just mean numbers, right? Roots. But these poles, when you add something, add a component, you are in a sense adding a pole or a zero. For example, when you bring in, this J, you see this J is directly affecting the pole, right? Based on what value of J you choose, this will have a different response. So you can, in a sense, you can choose certain values of D and J to get any kind of response here, right? You can choose a value of J and D such that it increases only in the real axis, or it can increase only in the imaginary axis, or you can keep the damping ratio the same by choosing an appropriate ratio of J and D. You see it? And now you're able to connect the real world and the real world control system and the math behind it. And that is what you need to learn about time response. Respond. And it directly relates to math, which is, the math here is, a lot of emphasis is on these poles. Okay? Your poles determine how your system is going to react. And every time you add a component, you learn. So if you look at a general control system, you'll have a system, okay, here. You'll have, so this is your plant or system, plant or process. Then you'll have an actuation system. Then you'll have a control system. Okay? Now you see, you'll be able to, you can always determine this could be, in an aircraft, what is this? This is really the vessel, not really the aircraft, but the vessel you want to control. Now, what are your actuators? Actuators are actually your ailerons or radar. Those are actuators, right? Those will impact your vessel. These two together form the aircraft, so to say. Now, if this was not the actuators, now you could attach a control system to this actuators and get the output of this to sense, to get to a particular response, right? So this, you're expecting the altitude of this or the speed of this to be certain value. And that is what this is trying to control, okay? Now what is happening here is, you should understand is, this could be a second order system, okay? But when you add this, when you add that actuator itself will have its input-output relationship. So you're adding poles and zeros. Now your control system becomes a little more complicated, or the system which needs to be controlled becomes a little more complicated. Now you bring in a control system, you're adding more poles and zeros, right? You see that? To the whole system. Now you are talking about the response, because the control system itself is embedded in that, this thing, right? Right. Right. So control system is essentially going to actuate or going to guide the actuators. Actuators is going to actually act on the vessel or the plant, and the plant is going to respond accordingly, right? So you could, this control system could be a human being, but as part of this course we try to study it as automatic control, right? So when you add something like this, you are increasing the complexity and essentially you are adding more poles and zeros. Overall the system changes, and this could have many more components. For example, you have actuators, but this is the general figure, okay? Now, a disturbance could creep in, right? These are subsystems, okay? But there are signals as well. Now, when you're actuating, you cannot assume the actuators are only going to get commanded by the control system. The actuators, if there is high wind, actuators are obviously going to get affected by that, right? So that also you should take into consideration. That is like a signal, right, coming in. Apart from the control system itself, whatever the control system is commanding, there's going to be some signal coming into the actuators. You have to be able to ignore that and just, so these actuators, when they do that, you cannot really, the plant is not going to ignore that because it's dynamics. It is going to get affected by that, the disturbance. So this has to compensate for the disturbance plus the desired response or the desired output. And this is how you start thinking about control systems and systems. And the foundation of if you want to study control systems as control engineers, you should understand dynamics, because you cannot otherwise design a control system. There is no way you're going to design a control system if you don't completely understand the dynamics, which is, again, comes back to physics. Okay? And these poles and zeros play a very vital role, even in very complicated systems today. Aircrafts are very complicated today, right? Still, much of the design is based on poles and zeros. Although mathematically you could implement very complex control system algorithms. But when you physically transfer it to implementing, it again translates to poles and zeros, or what we'll be studying called PID, proportional, integral, and differential controls. It's essentially a way of affecting the poles and zeros. Okay, so these poles and zeros. So we saw poles and zeros in the context of transfer function, right? In the context of transfer function, what are poles and zeros? Right. So the roots of the denominators are poles. The roots of the numerator are zeros, or values of S which will make the system go to infinity are poles. Values of S that will make the system go to 0 are zeros, right? If we start talking about what is the other modeling you have done? What is the other technique you have learned? Transfer function was frequency domain modeling. State space. So what are poles in the context of space, state space? Before going to state space, in the context of differential equation, what are poles? Anyone? Part of the solution, you have to be part of the solution, but what are they? For example, we said roots are the poles, roots of the denominator are poles. Okay. So we looked at this, right? Your response could be something like, so this is time domain response. We said this plus 2 e to the power of minus phi t, correct, plus 3 over phi e to the power of minus 6t. So these, you see these, the coefficients, those correspond to poles. So what you see, what is happening? If you just look at this is a first order system, right? This is a solution, only this is first order solution, correct? So this would be second order solution. You see that? And you should understand that what is the driving this thing here is this 5 and 6. Okay? So what would be the corresponding solution would look something like this. 2 over 5s plus 2 over 5 s minus s plus 5 plus 3 over 5 s plus 6, right? So you see the roots here are minus 5 and minus 6, and those directly correspond to and 0. So those directly, so this is your forced response and this is your natural response, right? So we said this was our natural response. Anything that is exponentially decaying is generally regarded as natural response. And this is a forced response because this comes from the input. Input is if something is exponentially decaying and as time goes to infinity, this response is going to become 0. As time goes to infinity, this response is going to become 0, and the response or the output is majorly characterized by the input at that point. Okay. So in the context of differential equations, this is what your poles and zeros are. The solution to differential equation, it is part of solution, but this is what correspond to the poles. Okay. in the context of time domain modeling, is something called eigenvalues. You heard about eigenvalues, right? So if your system is of this form, x dot is equal to ax plus bu, and y is equal to cx plus du, the poles or eigenvalues if you take the determinant of Si minus A and set it equal to 0, that will give you the eigenvalues or the poles of the system. Okay? See, if you look at this, this is the system matrix, right? And the poles should reside in this. That is because poles are part of the system. They cannot reside in this because this is the control matrix. Okay? This is the output matrix. And this is again the output matrix which affects the control matrix which affects the output. Okay? So they will most certainly have to be in this system matrix. And the values of the eigenvalues which are going to make this matrix equal to 0 would be the poles. Okay? So for example, we can derive this, but I think let's not do that. We'll just take this. If you want the derivation, I can give you the derivation of how we get here. Okay? But for assignment and for exam, I would like you to remember this or just note it down on your formula sheet. So if you're given such a system, I'll just give you an example. Huh? You had a question about that? So if you have something like this, x dot is equal to, so I'll just make up this, okay, 0, 3, 4, 2, 0, 2, 2, f of t, and y is equal to 1, 0, x. Okay. You'll be, let's say you're given such a the state space model of a system. Okay. And you're required to find the poles of the system. So what do? You just build this matrix. So what is Si minus A? If A is, what is the order of A here? it's a 2 by 2 matrix, right? The order is 2 by 2. So your Si minus A, you build Si minus A like this. Have the S variable multiplied, element-wise multiplied by identity matrix, okay, minus, and I think we have done this in the lab, right? 0, 3, 4, 2. Okay, so this would be S minus 3 minus 4 and S minus 2. So your Si minus A is essentially this. Got it? And all you need to do is you need to take the, so you have S, and you when you do the minus, what you do is you just do element wise, right? So S minus 0 is S, 0 minus 3, 0 minus 4 is minus 4, and S minus 2 is S minus 2. Okay. If you take the determinant of Si minus A, these would be the poles of the system. Okay. And you can actually verify. So what is the determinant? It is S into S minus 2 minus 12 equal to 0, right? So you have a square plus minus 2S minus 12 equal to 0. So what are the poles of this? So this should be the denominator, correct, for the system. And what is it, let's say, what is the transfer function of that system? The transfer function of that system is, you have x1 is the output, so you can say x1 over s over f of s equal to, would be 2 or it would actually be s square minus 2s minus 12. If you look at it, so you have, this is x1 and x2, right? So it would be, obviously this is x and x1 dot. Right. So you have x1 dot is equal to 3s, okay, and x2, so you have x1 dot is equal to 3, let's do, x1 dot is equal to 3 x2, okay, and x2 dot is equal to 4x1 plus 2x2. Okay. So you have we'll simplify this a little bit. We'll do 1, okay, 1, 1, so we have -4, so you see this x, this is x double dot of t is equal to plus f of t, okay. So this x double dot of t is minus or plus 4 x of t plus 2 x dot of t, okay, and if you just plus f of t, so you can see these two are essentially this. If you move things over here, you'll see that. So let me do it again. So you have x1 dot is equal to x2, right? Which is, that's it, okay. And x2 dot is what? It should be x double dot, right? This is equal to x1 dot is x dot of t, which is equal to x2, okay. x2 dot is x double dot of t, which is equal to 4x1 plus 2x2. This is equal to 4 x of t plus 2 x dot of t. Think about these as these, okay. Now it makes sense. You should be able to distinguish between state variables and system variables. Okay, now it makes sense. A little more. Okay, but I think if you try it yourself, you'll understand it. Okay, z1 dot, your state variables, this would be z, simply. So you have z1 dot, z2 dot, and this is z1, z2. Okay. Have to get going? Okay. But this will give you, this is important, and I want you to make sure you understand this. The determinant of Si minus A will give you poles of the system. Okay. We'll discuss a little bit of this in the next on Tuesday. By the way, there will not be a class on Monday. What I'll do is I'll post a video instead, maybe like a 15-20 minute video. Huh? you can turn in the homework. I'll be here on campus, but I won't be able to come to the class. Okay. Huh? No, only for this class.